Jai Hind everyone. I am Vivek Kumar Pansari, Assistant Professor in Department of Mechanical Engineering at Ajay Kumar Garg Engineering College, Ghaziabad. In my previous video related to shear force and bending moment, I discussed the basic concept related to shear force and bending moment. What is basically the shear forces, what is bending moment, what is the sign convention for shear force and bending moment, and what effect it causes on beam. So, all these things and how these shear force and bending moment both terms are interrelated, and when we are going to deal with the problem related to shear force and bending moment, and we are trying to draw the shear force diagram and bending moment diagram, then in that condition which type of shape of diagram will be. So, all these things has been already discussed in my previous video related to this particular topic. So, in this video I would like to come with some problems, so that whatever we discussed there, now it will be applied in the form of numerical problems. So, then the concept and numerical problems by watching both the videos will be clear. Okay. So, the first problem is related to a simply supported beam subjected to uniformly distributed load. Okay. So, here we are observing that there is a beam of length L which is subjected to uniformly distributed load W per unit length intensity. Okay. So, by the symmetry of this beam and the distribution of load, we can say the support reactions will be WL by 2 and WL by 2. So, there is nothing very great about this. This is WL by 2, WL by 2. We all know how to find out the support reaction. Now, I am coming to the point of shear force. Okay, how to calculate the shear force. So, shear force is basically what? If we go with the definition of shear force, it is the algebraic sum of all the forces acting either side of the section plane. So, here I have selected a section plane XX, okay, at the distance x from one of the support. Okay. Now, definition wise, it is the algebraic sum of all the forces either side of the section plane. So, on the left side of the XX plane, we are observing two forces. What are these two forces? The first one is WL by 2, this is the support reaction. Second one is this much of UDL, which is on the left side, So, we can write the shear force at section XX, this will be algebraic sum WL by 2 minus WX. WL by 2 is the support reaction at support, and WX is the intensity, is the load due to the UDL on the left side. Left side upward forces we are considering as positive, and left side downward forces we are considering negative. So, now the equation is like this, ki WL by 2 minus WX. Okay. So, this is what the equation for shear force, and this equation is valid from this support to this support, because we are not observing any other change in between the beam. The loading condition, loading pattern is similar. So, the one equation is sufficient here. Okay. So, now we can find out the shear force at different points. Shear force at x equal to 0, it means on this particular support. So, put x equal to 0, it will be WL by 2. Shear force at another support, so put x equal to L, it is coming out minus WL by 2 in this equation, and in between at the midpoint at x equal to L by 2, the shear force will be getting 0. So, now we are having the values of shear force at different points at supports and at the midpoint. Another important thing which we can observe from here, ki the equation, the type of equation which we are observing here, the type of equation is y equal to mx plus c. It is an inclined line equation. Okay. So, it means when we are going to draw the shear force diagram for this particular beam for this particular loading condition. So, the shear force diagram will be the inclined line. So, as we discussed in last video, whenever the section of beam, portion of beam is subjected to uniformly distributed load, then the shear force diagram will be inclined line. Now, come to the bending moment part. Bending moment, the definition wise, mathematically it is the algebraic sum of all the moments acting either side of the section plane, okay. And moment will be because of what? Moment will be because of the forces. So, here we are observing two forces on the left side. What are these two forces? WL/2 and WX. These are the two forces acting on the left side of the section plane. So, WL/2 will cause some rotational tendency about XX, and this WX will also try to create some rotational tendency about XX. How much will be the rotational tendency of this WL/2? I am writing WL/2, this is the support reaction, and the perpendicular distance of this from XX plane is X. So, WL/2 into X, and the tendency is clockwise, which I am taking positive because of the UDL. So, the value of UDL is Wx, which is on the left side. It will be effective on the midpoint of it, on the midpoint of it. So, this particular distance will be how much? It will be x by 2. So, Wx into x by 2. This will be the bending moment equation. Let us see what is written over here. Yes, the similar equation is written over here. Okay. WL/2 into x, it is because of the support reaction, and Wx into x by 2, it is because of the UDL, which is on the left side of the section plane. Now, the equation is available with us. Now, this equation is also valid from support to support. Okay. So, at x equal to 0, bending moment will be 0. At x equal to L, put the value L here, it will be 0. And at x equal to L/2, at x equal to L/2, it is coming out WL square by 8. It is coming out WL square by 8 by putting the value here, WL square by 8. It will be positive. It will be WL square by 8. Okay. We can observe the equation. It is which type? Parabolic type. Quadratic equation is there. We can observe WL/2 into x minus WX square by 2. So, the shape of curve is also known. Parabolic curve will be there. Now, we can draw the shear force and bending moment diagram. As the shear force equation is inclined line equation, at this point it is positive, at this point it is negative, at midpoint it is 0. So, inclined line of negative slope, inclined line of negative slope, inclined line of negative slope is there. Okay. And the bending moment diagram is 0 here, 0 here. At the midpoint it is WL square by 8, the nature of curve, okay, opening downward because minus x square term is there. So, WL square by 8, WL square by 8. One more thing which we can observe from here, that is the relation between the shear force and bending moment. What it is? It is F equal to dm over dx. So, the point where shear force is 0, it means this point. Here shear force is 0, bending moment will be either maximum or minimum, the condition of maxima and minima. So, these things which we can observe from here already discussed, but when we are doing the numerical problem, then things becomes more clear, things become more clear. So, I hope this particular easiest type of the problem was there. So, it is clear. Now, we are moving to some more complication. So, here what we are observing? We are observing in this problem that there is a UVL, uniformly varying load. The load is increasing with uniform slope. So, from 0 to 6 kilonewton per meter it is varying. Okay. So, as we know how to find out the support reaction. So, the support reactions we can get R1 plus R2 equal to 36. R1 is the support reaction here, R2 is the support reaction here. So, R1 plus R2 we can get 36. Now, for finding out the support reaction, we can take the moment. I am not going how to write the moment equation here because already discussed in many problems. So, R1 is coming out 12 kilonewton and R2 is coming out 24 kilonewton. Now, we are interested in shear force and bending moment of this. So, let us come to that particular point here. Okay. What we did? We did that a section XX at the distance x has been selected. Okay. Now, at this section plane, what is the value of shear force? So, obviously, by the definition of shear force, it is the algebraic sum of all the forces acting either side of the section plane. So, on the left side of the section plane, what are the forces? We are observing that there is one 12 kilonewton support reaction and this much of UVL, Now, how to find out that this UVL? This will be the area of the triangle. So, what can I write? Half into x into, this is what? W. I am saying this is what? W. So, W is not known. Is this W is known? No, this W is not known. So, for finding out W, we can apply the concept of similar triangle. Similar triangle between which two triangles? O, A, B and O, C, D. These two triangles are similar. So, W upon 6, the ratio of their perpendiculars and ratio of their base, x upon 12, the span is 12 meter. So, x upon 12. So, this W is coming out x by 2. So, now we can go with this. So, half into x into what is it is? It is x by 2, it is W equal to x by 2, it is coming out W equal to x by 2. So, what it is coming out? X square by 4. So, this is the value of what? This is the value of load. This is the value of load which is on the left side. Which load? UVL load. Load of UVL. So, it is coming out either by taking the average or by taking the area of the triangle. Okay. So, this point. Now, come to the shear force and bending moment equation. Shear force is the algebraic sum of all the forces either side of the section plane. So, on the left side of the section plane XX, there are two loads. One is the 12 kilonewton which is upward. So, it will be treated as positive shear force, and this x square by 4 which is the area of this triangle or the load of this UVL which is on the left side of the section plane, it will be downward. So, it will be treated as negative. So, 12 minus x square by 4, 12 minus x square by 4. Now, we can observe here, what we can observe, that as the load changes from UDL to UVL, the equation changes from inclined line to parabolic equation. So, now the shear force curve will be parabolic. Now, come to the bending moment equation. Bending moment equation, the moment due to these two loads 12 and x square by 4. The distance of 12 kilonewton load from section plane, this is distance of this is x. So, 12 into x, it is clockwise, in nature, and because of this triangle, now I am making this triangle, this x square by 4, this is the load is x square by 4. What will be the distance from here? It is 2x by 3, and from the section plane it will be x by 3. Okay. When I am converting this UVL which is on the left side of the section plane in a single point load, it is x square by 4, and the position of this load is 2x by 3 from initiating point and x by 3 from the section XX. So, now we can take the moment also. So, 12x into minus x square by 4 into x by 3. So, now both the equations are available. Bending moment equation is cubic. Now, again we are not observing any change. The load intensity is uniformly increasing. So, the one section will be sufficient here. So, it means it is valid from start point to end point of the beam. So, we can put these values. So, at x equal to 0, it is shear force is 12 kilonewton. At x equal to 12, it is minus 24. Okay. And for finding out the bending moment, at x equal to 0, it is 0. At x equal to 12, it is 0, and the point where shear force is 0, at this point the bending moment will be maximum. So, by putting this equation equal to 0, we can find out the value of x. So, in order to find out the point where shear force is 0, so 12 minus x square upon 4 equal to 0. So, by this we can get the value of x equal to 6.92. When we are putting this x equal to 6.92 in this equation, we are getting the maximum value of bending moment in this beam, and this is what the diagram, shear force diagram, as the equation of shear force was quadric. So, the curve is also quadric. This is the point where the shear force is 0, and at this point the bending moment will be maximum. So, this is how we can draw the shear force and bending moment diagram for different type of loading. Okay, I hope this is also clear. One UDL case I have taken, one UBL case I have taken. Now, sometimes if somebody is having problem in writing the equation in form of x, then there is one direct method which is basically used for checking the problem, because here we have to remember many things, many concepts, but although for checking the problems, because I did correctly or not, we can use this particular method also, which is known as direct method. Okay. So, now we are seeing a much larger beam which is loaded with multiple types of load. So, a beam is there A, B, C, D, E, F, G. Between A, B there is a UDL of 20 kilonewton per meter intensity. At B it is supported by a simple support. At C there is a load of there is a pure moment of 100 kilonewton meter. At D 50 kilonewton. At E it is supported by simple support, and at F there is a point load of 40 kilonewton downward. Okay. So, first step for dealing with this type of problem, which type of beam it is? It is a overhanging type of beam, because part AB and part EG is hanging. So, okay. So, supports are not at the extreme end. So, we can say it is overhanging type of beam. The first step to deal with this type of problem is to find out the support reaction. So, for finding out the support reaction, we can write two equations. First is related to sigma Fy equal to 0. So, Rb and Re, there are two support reactions which are upward, and there are loads 20 into 0.5. This is what the UDL acting downward, 20 into 0.5, because of this 50 this point load and 40 this. So, all these loads. So, Rb plus Re equal to this, and one more equation is required to take the moment about point B. So, to take the moment about point B, we can go with Re into 4.5. So, Re, the distance from B, 1, 2, 3, 4.5, and the tendency of rotation will be anti-clockwise. 20 into 0.5, 20 into 0.5 into 0.5 by 2. This is because of the UDL. So, 20 into 0.5 is the net effective load of this UDL, and 0.5 by 2 is the distance from point B, plus 100 plus 100, this pure moment. All these are anti-clockwise. So, taken on the one side. 50 into 3, this is because of the 50 kilonewton load at point D, and 40 into 5, this is because of the load at F, which is at 5 meters of distance, and this is the clockwise. So, by solving these two equations, we can find out Rb and Re. So, Rb is coming out 45, Re is coming out 55. Now, direct method for calculation. Now, what we have to remember? We have to remember, as and when we are getting UDL in the beam, the shear force diagram will be inclined line, bending moment diagram will be parabolic, bending moment diagram will be parabolic. As there is the effect of point load, the shear force diagram will be constant horizontal line, bending moment diagram will be inclined line. So, these things we have to keep in mind. But anyways, the direct method is shorter and simpler to check the problem. So, we can do one problem related to that. Now, start with the point F. Now, start with the point F, or even though we can start from G. So, at G, is there any load? No, there is no load. There is no load. So, we can say no load at G. So, shear force is 0. Sign convention we can select accordingly. Either if we are considering the left side upward force is positive, then according to that also we can draw, or one more convention we can take the opposite convention, opposite sign conventions also. Okay. At point F we are observing what? We are observing there is a load of 40 kilonewton and which is acting downward, and it is on the right side of the beam. So, minus 40. So, here in this problem the sign convention is different, sign convention is opposite. So, no problem at all. The shear force diagram will be the mirror image of the diagram which we are generally observing. So, we must be used to both type of sign convention, there must not be any problem. Okay. So, here the sign convention is this, the right side downward will be treated as negative. So, we have minus 40 kilonewton. Now, we are coming to the point E. So, at point E, on the right side of the point E, up to point E there are two forces, minus 40 that is at F and 55, this is the support reaction at E. So, minus 40 plus 55, algebraic sum of the forces. So, it is coming out 15 kilonewton, it is coming out 15 kilonewton. Now, move to the point D. So, shear force at point D, the forces at D and on the right side of the D, algebraic sum of all these forces. So, minus 40 plus 55 minus 50. So, this is coming out 15 minus 50 which is minus 35. Now, at point C, as there is no force, so it 100 kilonewton meter is the pure moment, so it will not be counted for shear force calculation. Now, at point B when we are coming, so the algebraic sum of forces at B and on the right side. So, minus 40 plus 55 minus 50 plus RB. So, it is coming out plus 10. And at point A, if I take the algebraic sum of all the forces, or from the left side if I am writing the calculation, then it will be 0 at point A. So, this is what the shear force calculation. Similarly, we can go for the bending moment calculation, as G and A, these are the extreme points. So, at these two extreme points the bending moment will be 0, mg, mf, the bending moment will be 0. At F also it will be 0 because there is no force on the right side of this, as there is no force on the right side of this. So, if there is no force, there will be no rotational tendency. So, at point G the bending moment is 0, at point F also the bending moment is 0. Now, come to the point E. At point E, what are the forces? There are one force 40 and the distance of this 40 from point E, it is 0.5. So, 40 into 0.5, sign convention negative. Okay. So, 40 into minus 20 kilonewton meter. E, RE will not be taken into account because it is passing through point E. So, the bending moment, there will be no rotational tendency because of RE about point E. Now, come to the point D, algebraic sum of all the moments due to forces either on D or on the right side of the D. So, 40 into 2, 40 into 2, 55 into 1.5, RE into 1.5, and this 50 will not create any rotational tendency because it passes through point D. So, no rotational tendency about point D. So, now this is coming out 2.5 kilonewton meter. Similarly, we can go for the this point C also. So, minus 40 into 4, 40 into 4, 55 into 3.5, 50 into 2 and 100 and 100. So, these, if we are considering the right side of the point C, if we are considering this equation is written for the right side of the point C. If we are moving beyond the point C, then this 100 kilonewton meter will also be in account. This 100 kilonewton meter will also be in account. So, the equation will be which type? Equation will be, this will be minus, I am writing for the left side of the point C, minus 40 into 4 plus 55 into 3.5, then minus 50 into 2 and plus 100. So, when I am taking plus 100, then this is coming out plus 32.5 kilonewton meter. Why there is a difference? Why we are getting two values at point C? Because when I am dealing with this point C and I am considering only the right side of the point C, then this 100 kilonewton meter pure moment will not be in account. But as I am moving just left of the C, then this 100 kilonewton meter will also be the part of calculation. So that is why I have taken it. According to the sign conventions, I have taken the sign and find out. So this is coming out 32.5. At point B, we can write the equation in similar manner. Okay. As now all the values are available, now we can draw the shear force and bending moment diagram. Shear force here it is 0, between A to B, UDL is there. So the inclined line will be there. There is 10 kilonewton at point B, 10 kilonewton at point B. Okay. Then at point B, because of the support reaction, we are having two values. Okay. So 10 and 35, 10 is positive value, 35 is negative value. Then between B to D, we are not observing any other force, so it will remain constant, At point D, because of the point load, we are having two values, minus 35 plus 15, so minus 35 plus 15, these are the two values. Between D to E, as there is no other force, so it will remain constant. At point E, again there is a support reaction, so we will be getting two values of shear force on the left and right side, so plus 15 and minus 40. Between E to F, there is no force, so it will remain constant. Between F to G, it is 0, so 0. Similarly, we can go for the bending moment. At point this, it is 0. At this point, it is minus 2.5, and this will be parabolic. In the diagram, it is not very clear. It must be parabolic. Because the UDL is there, so bending moment curve must be parabolic. At point C, we can see the change, as we are getting two values at point C, minus 67.5 and plus 32.5, because there is a point moment. Okay, so minus 67.5 plus 32.5, and in the similar manner, as all other loads are point load, so the curve will be inclined line, and all the values are represented in this manner. So in direct method, we can say there is one issue, we have to keep this thing in mind. Equations are not supporting the shape of curve will be what. We have to keep this thing in mind, if the load is point load, then shear force diagram will be constant horizontal line, bending moment must be inclined line. If shear force diagram is inclined line, then bending moment diagram must be parabolic. So these things we have to. The calculations are totally typical mathematical numerical, no equation is supporting here. So, but for checking the problem, this method is okay. So I discussed both the ways, one how to write the equation, one how to check your problem, is it correct or not. So by both the ways you can go with the shear force and bending moment diagram problem. I hope by this particular discussion I have conveyed how to deal with the shear force and bending moment diagram. So thank you for watching the video, okay, and I hope your queries will be sorted out. So thank you very much. Thank you.